Welcome to the deep dive. Today we're tackling, well, maybe mastering is too strong a word, but we're diving deep into a shortcut for understanding Stephen Hawking's incredible book, A Brief History of Time.
It really is an amazing book. Back in '88 when it came out, I don't think anyone, certainly not the publishers, expected a book about, well, singularities and quantum gravity to become such a massive hit.
Exactly. It just tapped into this real desire people had to understand the big stuff. Hawking himself pointed out, didn't he, that it was on the London Sunday Times bestseller list for, what was it, 237 weeks?
That's the one. An incredible run. And he had that great summary of it saying he sold about one copy for every 750 men, women, and children in the world.
Huh, yeah. And the killer line.
Oh, absolutely. I have sold more books on physics than Madonna has on sex. Just brilliant.
Perfect setups. So our mission here is to trace humanity's picture of the cosmos, with Hawking leading the way, asking those huge questions. Where did we come from? Why is the universe like this?
We'll be starting way back with the ancient Greeks and pushing all the way to the edge of modern physics.
Okay, let's get into that history. And you have to start, really, with that wonderful story about the old lady and the tortoise, don't you?
Right. The astronomer gives his lecture, and she says the world's a flat plate on a giant tortoise.
And he asks, what's the tortoise standing on?
She just says, "You're very clever, young man, but its turtle's all the way down." It's a great way to show how older views sometimes just kick the can down the road on explanations.
But the Greeks, they started asking for more. Aristotle, around 340 BC, he was already making a case for a spherical Earth, and crucially, based on observation.
Yeah, he had two really neat arguments. First, the shadow of the Earth on the moon during an eclipse. Always round. That only really works if the Earth is a sphere.
Makes sense.
And second, he noticed the North Star seems lower in the sky the further south you travel. The Greeks even tried to estimate Earth's circumference from that, though. Their number was quite a bit off, about double the real size.
And Aristotle really locked in that geocentric idea, didn't he? Earth fixed at the center, everything else orbiting in perfect circles.
Yes, for sort of mystical reasons of perfection. Ptolemy then built that into a detailed model centuries later.
And that model stuck around for a long time, partly because the church liked it, right?
Yeah, exactly. It fit nicely with their cosmology, leaving room outside the stars for heaven and hell. But, the model had a massive observational problem.
Which was?
Well, to make the planets move right in his system, Ptolemy's calculations implied the moon should sometimes look twice as big as other times, which it obviously doesn't.
So they just ignored what they could plainly see.
Wow. Well, the model was useful for predictions and the worldview was powerful. But yeah, eventually the observations pile up. Copernicus, in 1514, comes up with the simpler, sun-centered idea.
But he kept it quiet initially.
Very quiet, circulated it anonymously. He was understandably worried about being called a heretic. The real observational proof needed telescopes.
Enter Galileo, 1609. He points his telescope up and sees
moons orbiting Jupiter. That was huge. It proved not everything orbits Earth. At the same time, Kepler was refining Copernicus's math.
Getting rid of the perfect circles.
Exactly. He figured out the planets move in ellipses, sort of stretched circles. That made the observations fit much better.
So the pieces are falling into place for a big shift.
And then comes Newton, 1687, Principia Mathematica. He provides the why. Universal gravitation. It explained Kepler's ellipses mathematically.
And Newton's laws fundamentally changed how we thought about motion itself, didn't they? It wasn't just about starting motion anymore.
Precisely. Aristotle thought you needed force just to keep something moving. Newton showed force changes speed or direction. His first law. No force, an object just keeps going straight at a constant speed. Inertia.
Which explains that famous experiment, the one Galileo supposedly did, dropping weights.
Right, or rolling balls down ramps. He showed, ignoring air resistance, heavy things and light things fall at the same rate. Seems weird, right?
Yeah, counterintuitive.
But Newton's second law explains it. A heavier object feels more gravity, yes, but it also has more mass, more inertia resisting that change in motion. The two effects cancel out perfectly.
And we saw that demonstrated perfectly on the moon.
Absolutely. Astronaut David Scott dropped a hammer and a feather, no air resistance. They hit the lunar surface at exactly the same time. Beautiful proof.
Okay, so Newton gives us this powerful framework, but it also starts to unravel some comfortable assumptions, like the idea that there's a fixed place in the universe.
Yeah, that's the problem of absolute rest. Newton's laws work just the same, whether you're standing still or on a smoothly moving train. Playing ping pong feels identical in both scenarios.
So there's no experiment you can do to prove you're the one really at rest.
Nope. which means no absolute space. This actually bothered Newton quite a bit. He believed in an absolute God, so an absolute space seemed natural. Philosophers like Bishop Berkeley jumped on this, arguing maybe space and time aren't real, just relative.
The philosophical headache.
Yeah.
And then comes another complication, the speed of light.
Right. Back in 1676, Ole Christensen Romer, a Danish astronomer, noticed Jupiter's moons seemed to get eclipsed slightly later when Earth was farther from Jupiter.
Ah, because the light had further to travel.
Exactly. He realized light had a finite, though very, very high speed. He even got a decent estimate for it.
Then fast forward to Maxwell in the 1800s.
James Clerk Maxwell, yeah. He unified electricity and magnetism, and his equations predicted electromagnetic waves, light, that travel at a very specific fixed speed.
Okay, but fixed relative to what, if there's no absolute space?
That was the puzzle. Physicists invented this idea of the ether, a sort of invisible medium filling all of space that light waves traveled through.
Makes sense, like sound needs air.
But then came the Michelson-Morley experiment in 1887. They built this incredibly sensitive device to measure Earth's speed through the ether.
And they found?
Nothing. Zero. Zilch. No matter which way the Earth was moving, the speed of light was always the same. It was a huge crisis for physics.
Killed the ether. Dead. So what was the answer?
Einstein, 1905, special relativity. He said, okay, let's just accept what Michelson-Morley found. The speed of light is constant for everyone. The only way that works, if motion is relative, is if time itself is relative.
Oh, so absolute time goes out the window too.
Done. Each observer has their own personal time, ticking at a rate that depends on their motion relative to others. It sounds bizarre, but it works.
And that leads to EMCA.
That's a direct consequence, yes. Mass and energy are interchangeable, and it also explains the ultimate speed limit.
Nothing faster than light.
Because as you approach the speed of light, your mass increases infinitely. You need infinite energy to go any faster. It's the cosmic speed limit.
Okay, so that's special relativity.
Yeah.
But Einstein wasn't done with gravity yet.
Not by a long shot. 10 years later, 1915, comes general relativity. He completely rethinks gravity. It's not a force pulling things across empty space.
What is it then?
It's the shape of space-time itself. Mass and energy, they tell space-time how to curve, and that curvature tells matter how to move.
Like a bowling ball on a trampoline warping the surface.
That's the classic analogy, yeah. Planets orbiting the sun aren't being pulled by a force. They're following the straightest possible path, a geodesic through the curved space-time created by the sun's mass.
And this theory made some testable predictions.
Oh, absolutely. Huge ones. It perfectly explained a tiny, nagging wobble in Mercury's orbit that Newton's theory couldn't account for.
What else?
The bending of starlight by gravity. Famously tested during a solar eclipse in 1919, Arthur Eddington led expeditions, and despite some iffy data initially, the results supported Einstein. Starlight passing near the sun was indeed bent.
And it even affects time itself.
Yes. Clocks run slower in stronger gravitational fields. This was actually measured precisely in 1962, comparing clocks at the top and bottom of a water tower. Tiny difference, but measurable. And it's absolutely crucial for things like GPS satellites today. They have to account for relativistic time differences.
It's mind-bending. This fabric of space-time, curved, dynamic, and everything limited by light speed. You mentioned the light cone.
Right. It's a way to visualize causality in space-time. Imagine time going up, one space dimension across. Light travels out from an event forming a cone shape.
So anything inside the future cone is what you can influence.
Correct. And anything inside the past cone is what could have influenced you. Events outside that cone, in the elsewhere, are causally disconnected from you right now.
Like if the sun vanished this instant.
We wouldn't know for about 8 minutes the time it takes light to get here. It's in our elsewhere until that light cone reaches us.
Okay, so the universe is vast, and we're limited by light speed. How did we figure out just how vast? Was our galaxy all there was?
That brings us to Edwin Hubble, 1924. He used certain types of stars, Cepheid variables, whose brightness relates to their pulsation period.
Like standard candles.
Exactly. By measuring their apparent brightness, he could calculate their distance. And he found other galaxies, island universes, vastly far away. Our Milky Way was just one of many.
And then came the realization that these other galaxies are moving away.
Yeah, pretty quickly astronomers noticed the light from distant galaxies was consistently shifted towards the red end of the spectrum. The Doppler effect.
Red shift means moving away, blue shift means moving towards.
Right. And almost everything was redshifted. And the farther away it was, the more redshifted it was. The universe wasn't static, it was expanding.
Incredible. But didn't someone predict this before Hubble saw it?
Yes. The Russian physicist Alexander Friedmann, back in 1922, he just took Einstein's general relativity equations and made two simple assumptions. The universe looks pretty much the same in all directions, and that's true no matter where you are.
Isotropy and homogeneity.
You got it. And just based on those assumptions and GR, his math showed the universe couldn't be static. It had to be either expanding or contracting. He predicted expansion years before it was observed.
And that idea of uniformity got a huge boost later, didn't it? Kind of by accident.
Totally by accident. 1965, Arno Penzias and Robert Wilson at Bell Labs. They were working with this super-sensitive microwave detector, trying to eliminate all sources of noise.
And they kept hearing this faint hiss.
Exactly. Coming from everywhere, day and night, no matter where they pointed the antenna. They even cleaned out pigeon droppings, thinking that might be it.
Huh. But it wasn't pigeons.
No. It was the cosmic microwave background radiation. The leftover heat, the afterglow from the Big Bang itself, stretched out and cooled over billions of years. Just as theorists like George Gamow had predicted, it was stunning proof the early universe was incredibly hot, dense, and uniform.
So from the Big Bang,
Hmm.
let's jump to the other end of a star's life.
Hmm.
The black hole. You said a star balances heat pushing out against gravity pulling in.
Right. Nuclear fusion in the core generates that outward pressure. Hydrogen fuses to helium, releasing energy.
But what happens when the fuel runs out?
Gravity wins, the star starts to collapse. For smaller stars, the collapse stops because of quantum mechanics, the Pauli exclusion principle.
The rule that says identical particles, like electrons, can't be squeezed into the exact same state.
Precisely. That resistance creates enough outward pressure to form a white dwarf. If the star is more massive, electrons get forced into protons, creating neutrons, and the neutron's exclusion principle pressure creates a neutron star. Super dense, but stable.
But there's a limit to how much pressure even neutrons can provide.
There is. The Chandrasekhar limit, named after Subramanian Chandrasekhar. If the collapsing core's mass is above this limit, roughly 1.4 times the mass of our sun for white dwarfs, or a bit higher for neutron stars, nothing known to physics can stop gravity.
And it collapses. To what?
To a singularity. A point of theoretically infinite density and zero volume where space-time curvature becomes infinite.
And around this singularity forms the event horizon.
Yes, that's the boundary. It's the point where the escape velocity equals the speed of light. Anything crossing that boundary, even light, can never get back out. It's trapped.
So if you were watching, say, an astronaut bravely falling into a black hole, what would you actually see?
From a safe distance. It would be very strange. As the astronaut gets closer to the event horizon, their clock would seem to tick slower and slower relative to yours.
Time dilation due to gravity.
Exactly. Any signals they send back would take longer and longer to reach you, and they'd be increasingly redshifted, stretched to longer wavelengths.
So they'd look redder and dimmer.
Redder and dimmer, yes. And they would appear to slow down, approaching the horizon, but never quite crossing it from your perspective. Their image would essentially freeze there, fading away over infinite time.
But for the astronaut.
For the astronaut, time passes normally. They'd cross the event horizon without necessarily noticing anything special at that exact moment, though tidal forces would likely be immense. After that, though, escape is impossible.
And the star itself effectively vanishes, leaving just the black hole. And this no-hair theorem you mentioned.
Right. It's a remarkable result from general relativity. Once the black hole settles down, it's incredibly simple. All the complexity of the original star, its chemical composition, its magnetic fields, it's all lost. The final black hole is defined only by its total mass, its electric charge, usually assumed to be zero, and its spin, its angular momentum.
Just three numbers. That's it.
That's it. A black hole has no hair, as John Wheeler famously put it. All that information about what fell in is seemingly gone.
Okay, but these singularities, both the Big Bang and inside black holes, they represent points where general relativity just breaks down. The math goes infinite.
Absolutely. It signals that GR is incomplete. At those extremes of density and curvature, you can't ignore the other great theory of the 20th century. Quantum mechanics, you need a theory of quantum gravity.
Which we don't have yet fully. But trying to combine them led Hawking to maybe his most famous discovery about black holes not being entirely black.
Exactly. Black holes ain't so black. This comes from thinking about quantum effects near the event horizon. Quantum mechanics says even empty space isn't truly empty.
It's filled with virtual particles.
Virtual particle-antiparticle pairs constantly popping into existence and then annihilating each other almost instantly. It's happening everywhere, all the time.
Okay, so what happens if a pair pops into existence right at the edge of a black hole?
Well, normally they'd just recombine, but near the horizon, it's possible for one particle, say the antiparticle, to fall into the black hole, while the other, the particle, escapes.
And the one that escapes, where does its energy come from?
Ah, here's the clever bit. The particle that falls in can be thought of as having negative energy relative to an observer far away. To conserve energy, the escaping particle must carry away positive energy.
Which comes from?
The black hole's mass, EM/CMP Sawyer. The black hole pays the energy cost for that escaping particle. So to the outside observer, it looks like the black hole is radiating particles like it's hot.
That's Hawking radiation. So black holes slowly lose mass.
They do. They evaporate over incredibly long timescales for stellar mass black holes, but they do evaporate.
And smaller ones evaporate faster.
Much faster and hotter. Tiny primordial black holes, if they were formed in the Big Bang, could be radiating very intensely right now, maybe ending their lives in a burst of gamma rays. We haven't seen that yet, but it's a theoretical possibility.
Okay, let's swing back to the Big Bang itself.
Yeah.
You mentioned the standard model had some problems it couldn't explain.
Right, three big ones. First, the uniformity or horizon problem. Why do regions of the universe that, according to the standard model, were never in causal contact, light never had time to travel between them, look almost exactly the same temperature like the CMB shows?
How can they coordinate?
Exactly. Second, the flatness problem. The universe's expansion rate seems incredibly finely tuned. If it were just slightly faster early on, everything would have flown apart too quickly for galaxies to form. Slightly slower, and it would have collapsed back on itself long ago. Why so close to the critical density?
And the third?
The origin of structure. The universe isn't perfectly smooth. We have galaxies, clusters. Where did the initial tiny density fluctuations, the seeds for these structures, come from? The standard Big Bang model doesn't explain their origin.
So how do we fix these?
The leading idea is inflation, proposed by Alan Guth and others in the early 80s. It suggests that in the very, very first fraction of a second, the universe underwent a period of hyper-accelerated exponential expansion.
It blew up incredibly fast.
Incredibly fast, much faster than the speed of light expansion of space itself. This solves the problems. While the region that became our observable universe started out incredibly tiny, small enough to have reached thermal equilibrium before inflation kicked in, inflation then stretched this tiny smooth patch to enormous size, explaining the uniformity.
Okay, solves the horizon problem. What about flatness?
Inflation naturally drives the geometry of space towards flatness. Like inflating a crumpled balloon makes any small patch on its surface look flat. It explains why the density is so close to critical.
And the structure?
Tiny quantum fluctuations present before inflation would get stretched to astronomical scales, becoming the seeds for galaxy formation. Inflation provides a natural origin for them.
Mind-blowing.
Oh.
But where did all this stuff, the matter and energy, come from in the first place? Doesn't inflation require energy?
This leads to perhaps the most profound idea: the universe as the ultimate free lunch.
Sounds good. How does that work?
The total energy of the universe might actually be zero. Think about gravity. It's an attractive force. You have to add energy to pull two objects apart against gravity. This means the gravitational field itself stores negative energy.
Okay.
Inflationary theory suggests that the enormous positive energy of all the matter and radiation we see might be perfectly balanced by the equally enormous negative energy stored in the gravitational field across the universe.
So plus E from matter, E from gravity, sums to zero.
Precisely. You can create matter and energy out of essentially nothing as long as you create an equal amount of negative gravitational energy to balance the books. Inflation provides a mechanism to do just that on a cosmic scale.
The universe bootstrapped itself into existence.
That's the picture it paints. Which brings us to the ultimate quest: unifying general relativity and quantum mechanics. And Hawking's most speculative, but maybe most profound idea, the no-boundary proposal.
This is where we get into imaginary time. What's the core idea here?
It's a mathematical approach trying to figure out the quantum state of the entire universe at the very beginning. Using a concept called imaginary time, where time mathematically behaves like another dimension of space, Hawking proposed that the universe might have a unique history that satisfies a no-boundary condition. Meaning, in this imaginary time framework, the universe is finite in extent, but has no beginning, no edge, no singularity where the laws break down. Think of the surface of the Earth. It's finite, but there's no edge you can fall off. The North Pole is a point, but it's not a boundary in the same way.
So if you go back in time in this imaginary set, you don't hit a singularity, you just sort of loop around smoothly.
That's the geometrical picture, yeah. And the implication is potentially staggering. If the universe's quantum state is determined by this no-boundary condition, then the initial conditions weren't arbitrary. They were fixed by the laws of physics themselves. There was no choice involved in setting things up.
So, as Hawking put it, God might have had no freedom at all to choose initial conditions. The universe is entirely self-contained.
That's the ultimate conclusion of that line of thought. A universe explained entirely by physics without needing an external creator to set the stage.
Wow. Okay, so stepping back from that precipice,
Yeah.
looking at this whole journey from Aristotle's spheres to quantum cosmology, what's the big takeaway?
I think the biggest lesson is just how dramatically our understanding of the most fundamental things, space, time, gravity, existence itself, has been overturned and deepened. We went from a small, static, Earth-centered cosmos to this vast, expanding, relativistic universe governed by quantum rules at its origin. And the quest continues, doesn't it? Trying to meld GR and quantum mechanics into that final theory of everything.
And Hawking leaves us with one last puzzle, related to time itself. Why does it seem to flow only one way?
Right. The fundamental laws of physics, for the most part, work just as well forwards or backwards in time. They don't have a built-in direction. Yet we clearly experience time moving forwards.
The arrow of time.
Exactly. And Hawking points out there are really three arrows we observe. The thermodynamic arrow things tend to get more disordered, entropy increases. The psychological arrow, we remember the past, not the future. And the cosmological arrow, the universe is expanding, not contracting.
And are they connected?
He argues strongly that the psychological arrow depends on the thermodynamic one. The process of forming a memory in your brain, which is creating order, requires you to expend energy and release heat, creating more disorder overall in the universe.
Yeah.
You can only form memories in the direction that entropy increases.
We remember the past because the past is more ordered than the future.
In essence, yes. And why do all three arrows point the same way? Why are we in an expanding universe where entropy is increasing? Here he invokes the weak anthropic principle.
The idea that the universe must be such that observers like us can exist within it?
Basically. Intelligent life, capable of asking these questions, can likely only evolve and exist during the expanding phase of the universe when there's a strong thermodynamic arrow creating enough order locally for complexity to arise, but enough overall expansion to prevent immediate recollapse.
So we see the arrows align because that's the only kind of universe or phase of the universe where we could see them?
That's the argument. It's a fascinating and perhaps slightly unsettling perspective.
It really ties everything together, this whole deep dive, this process of learning and understanding. It's creating order in our minds,
It
right?
absolutely is. But there's a cost, isn't there? As Hawking calculates, listening to something like this might add, say, 2 million units of information of order to your brain.
But
the metabolic process, thinking, listening, converting your lunch into energy, you radiate heat. You increase the disorder of the wider universe by something like 20 million units.
whoa, that's quite the exchange rate.
It is. That's the thermodynamic price of knowledge. Creating this tiny pocket of order requires contributing to the overall increase in entropy. It's the cost of understanding the universe.
A truly thought-provoking place to end. Thank you for taking this deep dive with us.